continue. So then we have seen for the Characterization method, we get the following flux function. So the numerical flux function of the Characterization method then becomes plus 1/2, we always focus on that, is then equal to 1/2. We take the average by taking the flux function f of our conservation law, evaluating that at uj, and add f of uj plus 1. And then we subtract. It turned out that this was delta x over delta t, uj plus 1 minus uj. So then we have this form of the Characterization method. If we apply this to the implicit Burgers equation, we will get the following. Equation. That was when we had the flux function. It's actually number 7 in the beginning. We have f of u is u squared half. Then we get the following. So it would be then the equivalent just for this case. We'll write it to see it. Fj plus 1/2 is 1/2 of the average of the fluxes, which are here uj squared half, then uj plus 1 squared half minus delta x over delta t times the difference of the conserved variable u, j plus 1 and j. So then we see that the numerical the numerical viscosity just for the flux is the following. The numerical viscosity, let's see that. So we always then divide by delta x to see that we have then here a derivative of the du dx that we approximate. And then this in front will get delta x squared over delta t, and we should not forget the 2. So we get then delta x squared divided by 2 delta t. So that is the numerical viscosity, only considering the flux, the numerical flux. When we do the modified equation approach, for the explicit discretization with that, we would also get a contribution from the second time derivative in the that appears through the approximation of the time derivative. But here, if we just focus on the flux, then we will see this immediately is this. And from this we can see the same problem that we already discussed for the linear advection equation of this method, the Characterization method. This method has a big problem when delta t gets small. When delta t gets small, this numerical viscosity gets large. We get very diffusive results. Of course, then this term here will get more and more dominating, and we get something that is like honey instead of without viscosity. So that is the dangerous thing with the Characterization method when the delta t gets small. So that means the method gets very dissipative. So we get a large dissipation error for small time steps. So when you use it, try to use it at the limit of the stability condition, which is the same as for the explicit upwind method. The truncation error of the method is order delta t and delta x under the condition that delta t over delta x is constant. Because this term here, delta x over delta t, will enter in the truncation error. We can get only that, neutralize that when we choose this constant. Then it's a first order method. If we don't do that, if we are careless about that, when delta t goes to 0 in another way, we can lose consistency. The stability condition of the method is the following. That is then for conservation laws, if we take that in the general form, we have 6 that were ut plus f of u x equal to 0. That is the following. It's the same as we discussed for the explicit upwind method. The maximum of the current number is then the maximum over all j of the characteristic speed, which is the f prime, the first derivative of f with respect to u. And that is u itself for the implicit Burgers equation. And that we multiply by delta t, so that is the distance that essentially the solution can travel at most in the time step delta t. That divided by delta x should be smaller equal than 1. So that is the stability condition. So that this should be smaller equal than 1. And in here, I just said it, we write it also, the f prime of uj is the first derivative of f of uj with respect to u. That is the characteristic speed. And for the implicit Burgers equation, this is u. So then we would have just uj here. Okay, so then we have a characterization of the Max-Rillich method. And not the least, the method is TVD. It is total variation diminishing. So the total variation does not increase with this method. But because of this problem with the numerical dissipation here, there has come up another method that is better suited, which does not have this annoying property, where we replace this here by something else. And the idea is originally from Rusanov. And the idea is then to take the characteristic speed, look what is the value at j and j plus 1, and take the largest value in absolute, the largest absolute value of those two. So then we have here a characteristic speed instead, similar to the upwind method, but instead of the upwind method, where we take that in a way that we get a conservative discretization, in a way, here it is just taken as the maximum of the characteristic speed at j and j plus 1. So that is the only thing. That is then leading to the Rusanov method, which in the US literature is usually called the local Lex Friedrichs method. So then we can just note that better than Lex-Friedrichs method is the Ruzanov method. Local Lex-Friedrichs method. And that has the following numerical flux function. That is Fj plus 1/2 is equal to, which is very similar to what we saw before. Essentially all of them have very similar pattern. First, the arithmetic average of the fluxes evaluated with uj and uj plus 1. You could say that is the central difference. Minus, and now we take the characteristic speed A in a certain way that we define shortly. Then uj plus 1 minus uj. That is the same as we had before. But the catch is now that we take here the characteristic speed and not delta x over delta t. Speed, modulus of that defined as the maximum of the modulus of the characteristic speed at uj and at uj plus 1. So that is then has no problem at all when delta t goes to 0. Delta t doesn't enter. For the inviscid Burgers equation, we have then the following. J plus 1/2 is equal to 1/2 uj squared half plus uj plus 1 squared half minus aj plus 1/2 uj plus 1 minus uj with the characteristic speed defined as following: uj plus 1/2, that is then entering, is then the maximum simply of the modulus of uj and uj plus 1. Of course, they are the characteristic speed. U is the characteristic speed. And we can see that the numerical viscosity, Newtonum, is equal to this characteristic speed modulus times delta x divided by 2. That is, you can say, well behaved for delta t to 0. No problem, as the Lex-Friedrichs has. By the way, you see here also nicely the dimension of the numerical viscosity. So it has a dimension of length squared divided by time. So if we had units, it would be meters squared per second. It is like the kinematic viscosity. So the methods that we have now been discussing, the Lex-Friedrichs and the Ruzanov, that is the one that we had here, both of them are TBD. that is a good property of both of them. So I mentioned last time computing the fluxes. And I want to say again, when you do the discretization, it makes sense to compute the fluxes beforehand. So when you have computed the fluxes everywhere, then you just use them when in the conservation form. So that means you have a vector f where you compute your fluxes, and then you have to number them, and then when you use them, then you just take them from the vector that you have. If you would compute them each time, you would then compute 2 times. Say for the cell J, you would compute the flux at J plus 1/2, J minus 1/2, or the neighbor, J plus 3/2, J plus 1/2. So you do it twice. When you compute it once in a vector, the fluxes, you have it only done once. So you can save the computing time when you do that. So when you just define a vector for the fluxes, for the numerical fluxes. So we have another method here that I want to mention. I don't want to derive it. You can look it up in the book. And it is actually similar to what we discussed for the linear affection equation. That is the Lax-Wendorf method. Just want to make sure that you have seen it. And you can see the derivation. Then you read about that in the book. Keep that as a remark. So the numerical flux function of the Lax-Wendorf method for conservation modes for 6, that is ut plus f of u x equal to 0 can be derived similar to what we did for the linear affection equation, and that was in our chapter 7, section 6, and then we get the following. Can you see that? Is that okay? Flux function fj plus 1/2 is equal to, we start again in a similar form as we always do, with the average of the flux function in our conservation law f, evaluated at uj plus f of uj plus 1 minus. Now it gets a little bit more complicated, but not too much. We have now delta squared divided by delta x squared, and then we take the characteristic speed that we get by f prime of the average, uj plus uj plus 1/2, and then we multiply, and that is a little different from the others, we multiply by the difference in f of uj plus 1 and f of uj. That. So that is then the flux function of the Lax-Wendorf method. That method is second order accurate. So the truncation error is of order, let's see, truncation error is of order delta t squared and delta x squared. So it means second order in time and space. It is stable for proteins, so we have the same condition that we had before, also for the upwind method and also for the Lex-Radix method, when that is smaller or equal than 1. But it is not TVD. So therefore it is not useful to use it when we have discontinuities. So there the other methods, although they are of lower order, they are only first order, they are better. But we can get these methods more accurate by a trick. And that trick I want to explain to you, because that is used almost in any CFD tool. You have a choice. You will find that under the name muscle. That brings us to chapter 5, higher order TVD methods. We have now seen first order TVD methods, upwind method, Lex-Radix, Rusanov method. Those are first order TVD methods, and how we can get them to higher order. So first order TVD methods, and I repeat it again, that was total variation diminishing. Total variation diminishing methods. Can easily be extended to higher order by what is called, and it is due to Bram van Leer, muscle approach. He did that when he was at the University of Leiden in the Netherlands. Now he has been for quite some time at the University of Michigan in the United States. And this acronym that he chose means the following. So muscle means monotone, upwind centered, schemes for conservation laws. Let's see. And the idea is actually coming from finite volume method. So we shall look now at the situation when we have X, U, we have here a couple of cells, and we focus on, this will be our grid point xj, xj plus 1, xj here we have what we call the faces. These are at the midpoints. This one will be at xj minus 1/2, and this will be at xj plus 1/2. So we shall now focus, say, on this cell J. Try to understand what is going on there. We imagine, let's see, that was here. That is wrong here. I wrote it actually wrong here, because this is now, it is at xj plus 1/2. Sorry for that. xj 3/2. So if we focus on this, we will focus on this here. So this would be then the xj minus 1/2. Between j minus 1 and j, we have the j minus 1/2, and between j and j plus 1 and j plus 1. Okay. So we imagine that we have some distribution here of our values, say at some time level n, and that we have here the uj minus 1, that we have here the uj, and that we go down here to uj plus 1, and that we have here say, let's see, we go here, here we are uj plus 2. So then we have here our different faces, and what we usually do is that we assume that we have really a constant distribution when we define what we want to compute here, our fluxes here. The fluxes here are usually defined in terms of the neighbor values, uj and uj plus 1. And in a way, we define a Riemann problem by the averages. And we assume that this is constant. We call this a reconstruction. So that is what we usually use. We use usually a constant reconstruction. So that is what is usually done. So the constant, we call it reconstruction. That means we have given point values, and from that we want to have a function. That we call a reconstruction. So constant reconstruction in cell J, that is, that would be xj minus 1/2 to xj plus 1/2. That means we have uj, now it's considered as a function of x, that is in uj of t in this cell. So we have given the uj only, but now we assume that we have this constant distribution in order to define our Riemann problem. And here we do it at j plus 1 in a similar way. So that is replaced by a linear reconstruction. And that we can imagine in the following way. We could also imagine it's a quadratic or higher order, but for the muscle approach we usually stay with a linear approximation, so that we say the distribution inside the cell J, that is indicated by this here, that is now equal to the value that we have in the midpoint of the cell, uj of t, plus x minus the midpoint of the cell xj times some approximation of the slope. We call it uj prime, where the uj prime is approximating the first derivative of u, say at the point xj. So that means then that we want instead, we want to have another distribution. we have to decide how we do that. One way could be that we take the slope from the left neighbor. That would be one option. We could also take it from the right neighbor. Let's take it from the left neighbor. So then we would have something like this. So then we would have this distribution here. So instead of this linear, we get instead of the constant, we get a linear distribution. Now if we take this and this here, we would have then this. We take this and this, we would get this. So instead of this these constant distributions, you would then get linear distributions. And in this way, we could imagine that we get a better approximation of the solution at the faces where we compute the fluxes. So the values that were before uj and uj plus 1 will then become these extrapolated values here. So that would then be, we would call that the uj plus 1/2 left, because then our value on the left side of the face, and the value that we have here, that would be the value that we have on the right side of the face. And we will then use those instead of uj and uj plus 1 to evaluate the flux. So that is the idea. So, what we can note, if we do it in this way, that the integral of the constant here is this area, or about the linear, they are preserved. So the conserved variables are not touched if we do this. We do this linear approximation inside the cells. So then, what we have said is that face that we concentrate here on the face. So it's also the name of the face that is the side of the boundary of between the cell j and j plus 1. That is called the face. So that at the face xj plus 1/2. We can get more accurate approximations. Then uj and uj plus 1 by uj plus 1/2 L and uj plus 1/2 right. So that is the idea. So that we assume by having a linear distribution in the cells, or linear reconstruction in the cells, we can get more accurate values at the faces. And from that, we then compute the numerical flux. Numerical flux is then fj plus 1/2 of uj plus 1 is then replaced by then 52 that we say we take, and then we take the same flux function, so that is not changed, but we put in the more accurate extrapolated values, which is then the uj plus 1/2 left and the uj plus 1/2 right. So that is the catch. these extrapolated values we can very simply get from 51. They are the following: the uj plus 1/2 L. Let us see that. Here we are in the cell J, and we want to get to xj plus 1/2. So then this distance here is delta x/2. So then we go by this, we add the slope times this distance, then we get this. So then we can get that there, then by getting from uj and adding delta x/2, and then this approximation of the slope that we still have to find. And the uj plus 1/2 right, there we have to go from the right cell, which is the cell j plus 1. To get here, we have to start here. So we take uj plus 1 here. So this will be then uj plus 1, uj plus 1. This will be then xj plus 1/2. This will be xj plus 1. So this becomes a minus delta x/2. And this will be then the uj plus 1. So we then have the uj plus 1 minus delta x/2. And this is then the slope in the cell uj plus 1. So now the question is, when we have this, how can we get these slopes? So that is now the point, how to get the slopes. When we have them, then we just put them in here, we compute this, and we use then this here, and UR, put that approximation in here, then we use this here as arguments for our numerical flux function, instead of uj and uj plus 1. That is all. So if you have a function for the numerical flux, you just feed it, instead of uj and uj plus 1, with the extrapolated values from the left and the right. That's all. So, but the question is still, how do we get these? So we have said in the beginning, if we just take the nearest neighbors into account, we can take it from the left or from the right neighbors. And it turns out we actually have to use both and find out about which one is the largest, if they have different sign or not. Because then, depending on that, we will choose the one or the other. For example, here, this is the cell J, right? In the plot here, we have taken the value from the left. We have taken the slope from here, uj minus 1 divided by delta x. That is the slope. We have used that here. We could also use the slope from the right, this and this. Then we would have this distribution here. But in this case, we see we have here a positive, here a negative slope. That indicates we are near an extremum. And in that case, it turns out we should not use either of them, but we should use 0. Because near an extremum, we should not use this higher order method, because that will lead to oscillations. So actually, in that case, we should rather choose the slope 0. So what we do is, so the question is how to choose slope uj prime. That is what we're discussing here. And we shall use it using a so-called limiter. So we have now two choices, and we shall limit the slope such that it will not lead to oscillations. So we choose the min-mod limiter to limit slopes. In that case, it would be uj minus uj minus 1 divided by delta x, and the other one would be the uj plus 1 minus uj divided by delta x. So we have, that would be for uj prime. So, and it does then the following. So then, in the first place, that would be in the cell J in our example, it would be, we would choose slope 0 because A, that is the delta x at uj plus minus 1/2, that is in that case uj minus uj minus 1, uj minus uj minus 1, that is positive, and the other one, the b, that is delta x, that would then be at uj plus 1/2, that would be the uj plus 1 minus the uj, this one is negative. So, in that case, it turns out we are near an extremum, and we should choose the slope 0 to be on the safe side. So that means then, when we do then this min-mod function, we would then choose the min-mod of these slopes dx uj minus 1/2 and dx uj plus 1/2. In that case, we would choose the 0. That means we would use the first order method, which we know works. At the other side, that would be in the cell J. In the cell J plus 1, the situation is different. Here we have a negative slope at the left side, and we have also a negative slope on the right side. But there we'll choose the one that is smallest in absolute value. So this one is smaller in absolute value than this one. So then we will choose this one. So that means choose then the slope that has the smallest absolute value. If both have the same sign. And here we would then choose, would be the min-mod. In that case it would be the delta x of uj plus 1/2 and the delta x of uj plus 3/2. So those are, this is j plus 1/2, this one, this is plus 3/2. We will choose this one is the smaller one in absolute value. This is dx of uj plus 1/2. And if we do that and plug that into then our approximation for the uj prime for the slope, we use this limiting and use then the extrapolated values to evaluate the flux, we get a higher order total variation diminishing method. So that we keep the total variation diminishing property, but we get second order away from extrema, where we use then a higher order approximation, a linear instead of a constant one, but at an extremum, when we have this situation, we get the first order method. So we get higher order, but at an extreme it is still first order. So I think we have to stop here over time. So we'll look at this a little bit more tomorrow, and then you will see it is a very easy thing to do, and you can easily get by that higher order. Okay.